In 5.5, we are looking at rational functions. Rational is a fancy math word for fraction. We are looking at fraction-based functions. So typically it's defined as f of x equals p of x over q of x. And what you have to understand about p and q is that these two are polynomials, independent polynomials. There's a polynomial on top and there's a polynomial on the bottom. And so these can be quite sophisticated looking and they can be quite simple looking, as in the case of this one to the right, f of x equals 1 over x. But we are simply looking at in this section how these fraction-based functions behave. Now, we're going to start filling in this t-chart here, this input-output table, because this function does some interesting stuff. So 1 over x, now it may not be clear, but 1 over x is a polynomial. It is a constant, 1, that is x to the 0 power. And so that really is a polynomial function, and x is also a polynomial function, meets the definition, but it's a very simple one, and we will add more sophistication in later videos. But to understand why this picture right here is the function of 1 over x, let's have a look at some of these input values. So the function of 1 over x, when you have an input of 1, that gives you negative 1/4. Negative 3 would give us 1 over negative 3, or negative 1/3. 1 over negative 2 is negative 1/2. 1 over negative 1 is just negative 1. Now what's interesting here is 0. 1 over 0 is an undefined value. We can't divide by 0, so it is not actually part of the domain. It's not an x value we can use, so there is nothing that goes right there. Now when we go to the positive side, 1 over 1 is 1, 1 over 2 is 1/2, 1 over 3 is 1/3, and 1 over 4 is 1/4. And if we start plotting these points, we have, let's do some easy, obvious ones, 1, 1, and at an x value of 2, it's at 1/2. And an x value of 3, we have 1/3. What you'll notice is this is getting smaller and smaller. Now, if I were to throw like 10 on here, like a positive 10, it's 1 over 10. Now, important things to note, that while this keeps going down and getting smaller and smaller, and if we extended it out, you would see it get closer and closer to the x-axis. It will never actually touch the x-axis, because even if I did 1,000, it would still be 1 over 1,000, which is in fact greater than the x-axis. It's greater than 0. Now, this thing is called an asymptote, and an asymptote is where you have values that get infinitely close to a value without ever actually touching it. If you ever had a sibling growing up and they were like, I'm not touching you, and you're almost touching them. They're like, I'm not touching you, but you're almost touching them. It's kind of like that. It gets infinitely close without ever actually touching. This line will get infinitely close without ever actually touching. If we do from the negative side, you have negative 1, and then negative 1/2, and negative 1/3 does the same thing, negative values, and it's also getting infinitely close to the x-axis, but it's doing it from the bottom, from the negative side. And so it once again gets infinitely close. Now the part that we're missing from this is this little chunk between 0 and 1 right there, and this part right here. So that piece, and I guess I should have made it this piece right here. And this part is where it gets really interesting, because if you notice, as the x values get bigger, it's getting closer and closer to the x-axis. But it actually, as the x values get closer to 0 right here, the values are getting really, really large. And let's look at why. So let's make another input-output table. But this time we're only going to pick values between 0 and 1. So here's what I mean. So we know that 1 has an x value of 1. But if we have an x value of 1/2, that literally means this. It means 1 over 1/2. It's weird for us to have fractions inside of fractions, so I'm actually going to write it like this. 1 divided by 1/2. These two are equivalent. Now, when you write it as in this horizontal orientation, maybe you'll see that we can look at this as dividing fractions. In dividing fractions, the algorithm is flip a second number and multiply. So this becomes 1 times the reciprocal of 1/2 is 2 over 1, which means this is just 2. This has an x value of, or an output value of 2. And if I said 1/3, that would be 1 divided by 1/3, or 1 times 3 over 1. It gives me 3. It's the multiplicative inverse. So 1/4 would be 4, 1/10 would be 10. I could go on from there. But what you're seeing is, as my values get closer and closer to 0, the output becomes infinitely large. You see this thing take off, going up and getting infinitely close to the x-axis. I'm sorry, to the y-axis, and getting infinitely high in its y value. It just skyrockets. We never actually get to the y-axis, but we do get infinitely close to it as this gets infinitely large. So as I said before, when you get infinitely close but don't actually touch, that's an asymptote. So this is another asymptote, another value where we get infinitely close without ever touching. So this never actually touches the x-axis, and it never touches the y-axis. We have a vertical asymptote, and we have a horizontal, oriented in a horizontal fashion, asymptotes. We have these two lines that we get infinitely close to, but never actually touch. So, looking at this very basic rational function, we can see that this does some really interesting things. And sorry, I didn't mention it, but as we go to the negative version of this right here, you'll see that as this is negative 1/2 and negative 1/3 and negative 1/4, those become super large negative numbers as we go down here, getting super, super negative. In subsequent videos, we're going to talk more about vertical and horizontal asymptotes and how they behave.